Hello everyone, welcome to the session 2 of unit 5 static timing analysis. In this session we will talk about the interconnects and delay calculation. Now the agenda is we will see what interconnects are, what are the various interconnect models. We will see the wire load models. There is some overlap with what we studied in unit 3, but there are a couple of more we'll go a bit more detail into wire load models. We'll look at parasitic formats and then we'll look at delay calculation. Now going back to the session 1 of static timing analysis, we learned that static timing analysis is of two parts. The first is the delay calculation and the second is the checking against the constraints. So it is the first part we'll concentrate on, the delay calculation part. Now delay again is comprised of two elements. So two elements are responsible for the delay. One is the cell, other is the nets. The cell delay comes from the library. We all know that. Actually, in the NLDM format. Yes, the delay is the delay numbers are represented in lookup tables, and a tool like PrimeTime just has to do interpolation based on the transitions, input transitions, and output loads. On the other hand, so the net delay, an STA tool does not have the net delay directly. It will always gather the value of resistance and capacitance of the net, and then it has to do the delay calculation itself using some method, some formula. So that is the concept we'll look at in this session. So a net, the properties of net are: net is a wire connecting pins of standard cells and blocks. So any two cells would be connected by an interconnect or a net, and a net obviously has only one driver. There are nets that have multiple drivers, but in that case consider a net that is being driven by let's say two drivers. One of them will be in a tri-state at any given point of time. So in effectively there should be only one driver on a net. What is a driver? A driver will be a cell. The cell will drive the net value to either 0 or 1 depending on the logic state. So it has only one driver for any effective calculation. Net can drive a number of fan out cells or blocks. So you can have on one side you have a driver, on other side you have the receivers. Now there is always one driver, but the number of receivers can be many. In that case, net will be segmented, obviously. So let's say a buffer is driving 4 other buffers. So there will be one net going from the output of the driver buffer, and then the net will be segmented, and then it will drive the different fan outs. Now this segmentation can happen in number of ways. Physically, I am talking about physical. Logically, it will be just one net. There's only one logical net from driver to 4 fan out receivers. But physically, the segmentation can happen at number of points. It depends on the routing, on the timing constraints, and so on. And then the net can travel on multiple metal layers of the chip. Now a chip is 3-dimensional in nature, in the sense that a chip is comprised of layers. So at the bottom you have the diffusion layer, the poly, which makes up the standard cells, and over and above that there will be metal layers going throughout the chip that will connect the drivers and receivers, that will connect the standard cells together. Now these metal layers are numbered like metal 1, metal 2, metal 3, metal 4, and so on. So a typical 65 nanometer process or a 45 nanometer process might have 6 metal layers or 8 metal layers, and so on. Usually there are about 6 to 8 metal layers in a particular process. So if metal 1 is horizontal, metal 2 will be vertical, if metal, and so on. So 2 consecutive layers will be vertical and horizontal to reduce signal integrity issues. So a net can travel on multiple metal layers of the chip, and it can be broken up into segments for equivalent electrical representation. We will see what segments are and how does STA tool uses those segments. This is just to make clarify the concept of a net. Now an interconnect will have three parasitics. Parasitic means unwanted. Parasitic by literally means something which is feeding off some a parasite is something that feeds on a host, or it's undesirable, not needed. So the R, L and C for an interconnect are undesirable. So we would want to use techniques to keep these numbers as low as possible, right? Interconnect resistance is between the output pin of a cell and the input pin of the fan out cell. Interconnect capacitance, every node, every input of a cell or every output of a cell or every net itself will have some capacitance with ground, and two nets running two nets will have some capacitance between them. This is called coupling capacitance. There is some interconnect inductance also which arises due to current loops, but the value is so low that it can be ignored. So for ASIC design, on-chip interconnects don't show significant inductance. Although on a PCB, since there are long wires running, they show a significant inductance and has to be taken into account for calculation. But when we talk about something that is fabricated on chip, the L value is not of any consideration. So we will only talk about R and C values. And why they are undesirable? Any resistance will consume power, will make the chip heat up. So obviously our target is to reduce the resistance as low as possible. This is why copper interconnect is very popular. Again, capacitance, the higher the capacitance, the more time, the more current needed to charge it up to VDD and then to discharge it to ground. So the more net delay. That's why again there are techniques to reduce capacitance. You would probably study in one of the fabrication courses. There are techniques to. So again, we talked about there are two types of capacitance. One is with respect to ground, other is with respect to the between two nets. So since we will, this is the reason why metal 1, let's say, horizontal, metal 2 becomes vertical, just to reduce this coupling capacitance. This coupling capacitance causes causes an effect which is called noise or glitch. We will see that STA tool also treat, sign off your chip for signal integrity issues. We will see what are those issues and how do we check for them. So that's why these R and C values are called parasitics. Now a typical interconnect will have a length L, and it will be represented as a distributed RC tree. What it means is that the trace of length L will be broken down into a number of R values, R and C values. So this is distributed RC tree, and now STA tool will employ some techniques to calculate the delay from this node to this node. Let's say this node is driven by a cell, by a buffer, and on this node there is a receiving buffer. So what STA tool will do, it will try to, so there will be a waveform here and there will be a waveform here. So what an STA tool will try to do, it will try to calculate delay between these 2 points. It will use some algorithm and it will try to calculate the delay for this distributed RC tree. In fact, delay calculation for nets takes much longer time when compared to delay calculation for cell. The only reason being that the cell delays are represented in a lookup table, and the only thing the tool has to do is interpolate. But in this case, it has to employ some sophisticated numerical analysis techniques to calculate a delay. Now we'll define few terms here. RT and CT are the total resistance and capacitance of this interconnect of length L. RT is equal to RP into L, CT is equal to CP into L, where the RP and CP are the per unit length values and L is the trace length. Now, so there are various models to represent interconnect. Some are more accurate, some are less accurate. The less accurate ones, obviously, it will take less amount of time to process through because there's less data. The more accurate the model is, the more time it will take the tool to calculate the time to calculate the delay. So one of the models is T model, in which total capacitance CT is model is connected halfway in the resistive tree, and the total resistance RT is broken down into two parts, RT by 2, RT by 2. This is called the T model. Other model is the pi model, in which the RT is in between two capacitances, and CT is the one that is broken down into CT by 2 and CT by 2. And RT is the total. There's some typo here. Total CT is broken down into CT by 2, and RT remains same. And then there is a much more accurate N section representation. It is more accurate. So when you keep increasing the value of N, it keeps on becoming more and more accurate. But obviously there has to be some limit, because the more sections you have, again the more compute intensive it becomes. So again it has two models, T model and pi model. So in both the models, CT is divided into CT by N, and RT is divided into RT by N. The only difference is that in T model, the first and the last value is RT by 2N, and in pi model, the first and the last value is CT by 2N. So these are just modeling techniques. So in effect, in physical effect, there is one single copper wire. Now there are multiple techniques to model it, and these models again, the more sections you divide it into, the more accurate it becomes, and the more compute intensive it becomes. This session is more about the available techniques to do this thing, but ultimately when we use prime time, when we go to static timing analysis tool, we are not worried about what model is used. The model used is dependent on what detailed parasitics have been fed into prime time, but otherwise we should not be concerned about what is the model used, whether it's a N section model, whether it's a T model or a pi model. Once we are given the parasitic data, we just read it into prime time, and then using report timing we can report the value of capacitance and resistance. But that value is the combined load. For example, the report timing report will show the combined value of capacitance at any pin. Right? It will not show the section information, because again it's just the way prime time will reduce things. It will calculate delay. We don't have to be. We can just read about it, but when we do static timing analysis, we should not be too concerned about it. Now let's see. In case of pre-layout SPA, when the parasitic information is not there, we use something called wire load models, which are used to estimate cap, R, the area overhead, and the length of the net based on the number of its fan out. Let's take one example. How do we do that? We've already seen that there are different wire load models in standard cell library. For example, here it is given, there are three models given: light, conservative, and aggressive. It also tells us for what area it is suitable, and so on. Now this is one example where a wire load model gives us some numbers. One is the resistance number. I think it should be per unit length. Capacitance number per unit length. Area per unit length. This is the slope of the curve. And now it tells us that for what fan out, what is the length. Let's say for fan out 1, length is 2.6, for fan out 2, length is 2.9, for fan out 3, length is 3.2, and so on. Using this data, what the tool will do, for each of the net, it will try to calculate the R and C and the length and the area value based on these numbers. Let's see how does it do that. Let me clear the annotation first. Yeah. Now let's see. Let's take a look at a net which has a fan out of 8. Now from the previous data, we see that for fan out length of 5, excuse me, for fan out of 5, the length is 4.1. This is the maximum that wire load model specifies. So for a fan out of 8, the tool will try to extrapolate. So for the value of 5, it is 4.1. So it uses simple a straight line formula to calculate the value at fan out of 8. So what it does is it's 4.1 plus 8 minus 5, which is this offset, into the slope. This is why slope is used to help the tool in doing the interpolation and extrapolation, right? So length is 5.6. Now based on this length, it can calculate the capacitance because it knows the length and the capacitance coefficient, which is 1.1. The resistance coefficient is 5.0. Again, we have got the value of resistance. Again, area overhead is length into area coefficient, and then so on. So this is how, based on the Y load model data, the tool is able to calculate for every net just by knowing the fan out. It will calculate the length, capacitance, resistance, and area overhead. Again, these are just estimates. The things change a lot when we go to post layout. Now, when we talk about Y load model for estimations, the tool will consider there are three. So first, it will choose a Y load model based on area, for example, and then it needs to know what tree type is targeted. So there are three tree types you can use. We'll see in the lab that we've already noticed this this term has come across when we saw the standard cell library. It mentions the tree type, either best case tree or worst case tree, and so on. So let's see what this tree type is. So in the best case tree, it is assumed that destination pin, the load pin, is right next to the driver. What it means is that there is no resistance from the driver to the destination pin, but the only thing being considered here is the pin capacitance, right? So that is why it is called a best case tree, because it assumes the resistance to be 0. So this R is not accounted for. All these receivers and the drivers, it's assumed that they are sitting next to each other and there is virtually no resistance. The only thing taken is the pin capacitance of each of the receiver pin. It is obviously an optimistic case. Second is the balance tree. Now in balance tree, the R and C is equally divided among all the receivers, all the fan outs. So the total R resistance being R wire, total capacitance being C wire. This section has R by N and C by N. This section has R by N and C by N. Again, same section has R by N and C by N. This is a balance tree. Worst case tree, what it assumes that the destination pin, each of the destination pin sees the complete resistance. This will only happen when the fan outs are the receiver cells are sitting right at the end of the wire, far end of the wire. So the first case assumes, the best case assumes that this receiver pin is sitting right next to this one. The balance assume that each of the fan out each of the receiver cell is at equidistant from the it is at equidistant point from the driver. The worst case tree assumes that all the receivers are sitting at the far end of the driver, and each of them will see the complete RNC. So obviously this is a worst case scenario. So the typical scenario will lie somewhere between worst and best, which is the balance tree. So again, this is a Y load model characteristic and not the real parasitic characteristic. This is what kind of layout is assumed, right? So usually you don't need to worry about it, and some of it is set in library by default. So when you do a report Y load model, you can see that what kind of tree is taken, or you can open up the standard cell library and see that. So this is the command to specify a Y load model. We've already seen that in design compiler. The command is exactly same for prime time. In that sense, actually in pre-layout, when we talk about the pre-layout stage, the design compiler and prime time, they behave exactly same, in the sense that most of the commands are similar, and the only thing different is that prime time is a much more advanced SPA tool. And when we want to work with real parasitics, we cannot work in design compiler. So there's the timing engine inside design compiler is faster compared to prime time. It has less features and it is more suited to synthesis. Whereas the prime time sign off engine is built for sign off at various technologies. It is much more accurate. It is the data, the calculation is matched with respect to spice, and it has lot more features to aid us in doing static timing analysis. But at a pre-layout stage, there are very few differences. So we have also seen wire load modes, top, enclosed, and segmented. I'll quickly revise them. The top wire load model, the wire load model of the top level is used for all the lower level blocks. In case of enclosed, the wire load model that is used for the design which encloses the complete net. So for example, in this case, WLM light encloses this complete net, so the wire load model WLM light would be used. The segmented wire load model divides the hierarchical net into segments, and a unique wire load model is used for each segment that depends on the design and under which this net is enclosed. For example, this part of the net is enclosed inside B3, and WL underscore AGGR is used for B3. So WL underscore AGGR will be used for this segment. For the second segment, WL right will be used. For the third segment, WL underscore TYPE will be used. So we have already seen this. That's why I went quickly over it. This is how wire load model is represented in the cell library. We've already seen this in Unit 3. I'll move forward. Now let's come to the actual parasitic data when we are working at the post layout stage. So where do parasitics come from? So first we give the synthesized netlist to the physical design team, or the guy or the person who's doing physical design. It can be you or it can be some other person. Now the design along with constraints is taken through the backend, the physical design flow. The first part of the flow is placement, then there will be clock tree synthesis, and then it will go through detailed routing. After routing, when the physical data is completely generated, GDS is generated, there are tools, extraction tools, which from the layout. Now the layout has all the information about all the nodes and cell placement, right? So these tools, one of the tool is called star RCXT from Synopsys. So this tool will read in the layout data. It will read in the technology specific files, which has the information that what is the thickness and what are the coefficients for different metal layers. Using that data, it will generate the parasitic file. Now these parasitic files can be in one of the three formats. Either they could be in the format DSPF, detailed standard parasitic format, or RSPF, reduced standard parasitic format, or SPEF, which is standard parasitic expression format. In one of these, so the tool will extract the data and it will put data into a file which will conform to one of these three formats. Now the most detailed format is DSPF. The format is same as SPICE. What it means is that each node is extracted. The R and C value will be present for each and every node, and obviously since it's represented in SPICE format, you can use any SPICE tool to read in and analyze. But again, at a full chip level, it will become very time consuming, and plus this file is huge. For even a simple design, this file might run into GB or hundreds of MB, right? Syntax is obviously too detailed because there is a lot of information here, and it is used for only very special cases where you want to see, when you want to do some SPICE analysis. SPICE analysis will be more accurate than prime time or any other static timing analysis tool. Again, it takes so much more time, right? On the other end of the spectrum is a reduced standard parasitic format, RSPF. In case of RSPF, the parasitics are represented in reduced form. So what is reduced? Not every node is represented. For example, take a look at this design where a CK buffer is driving two flops. Now in this case, it will be split into two parts, 1 and 2. Now the first part, this is called the driver model. A driver will be represented by, let's say, a pi interface, and then the receivers will be represented by again R and C values. And now at the receiver end, the driver will be reduced to a voltage source, voltage and current, a voltage source or a current controlled current source. This RSPF can also be used as an input to SPICE simulator. There are some limitations here. I think one of the limitations one is written here that bidirectional signal flow cannot be represented, and I am not sure if coupling capacity if it has coupling capacitance. I don't think it has. So it doesn't have coupling capacitance, so you cannot do signal integrity or noise analysis using this RSPF. And there is one format called SPEF, which is the most popular industry format for static timing analysis. Why? Because it is balanced in the sense that it is not as detailed as DSPF, but it has enough information. What it means that it has detailed parasitics up to some extent. It also has coupling capacitance, but it is of a similar format as DSPF, similar to the SPICE. It does not have every node, so it does. So the approximation is done at the level of the extraction tool. The extraction tool will make some approximations, or it will do some modeling, and it will dump SPEF which will be slightly less detailed than DSPF, but it will have the coupling capacitance also. So with SPEF we can do noise and signal integrity analysis. So this is the most popular industry standard format, and I also use this a lot in my on the chips I am working on. So again we talked about that every time our wish will be to reduce the interconnect resistance and capacitance both. Some ways are listed here. One of the way is to make the nets wider. A wider net will have lower coefficient of resistance. I mean, obviously the resistance of a net is inversely proportional to its area of cross section of the bit. So the more wider a wire is, the more current it can carry easily, and resistance goes down. Routing in upper thicker metals in a fabrication process, the metal layers at the top of the stack are wider and thicker, so usually have lower resistance, and most of the time they are used to route power signals and clocks, which are most critical in the design. So power signals are very critical. Why? Because an increased resistance on power signals will cause more IR drop issues. The more R, the more IR drop. That is why power signals will use the topmost routing layers to reduce the resistance to as much extent as possible. The top level layers are also used for clock routing because clock is a signal that goes globally. It fans out to so many registers, and the lower when clock you don't want to have signal integrity issues on clock. It will cause a lot of problems. That is why you use upper metal layers. So these are two ways. Either we use wider metals, or we use the upper metal layer. They are by default. Now let's see how do we read parasitics in prime time. So read parasitic command reads the parasitic data file either in SPEF or RSPF, or there's one more format called Synopsys binary parasitic format. It just converts the ASCII format. You can just read this any ASCII format parasitic file into prime time and into some in design and prime time, I think, and you can write out the binary parasitic format. So this the process of reading parasitics and mapping it onto design is called back annotation. And the read parasitics command by default it can recognize the file format from the file itself. So specifying the format is optional. Obviously, the net and instance pin name in the design must match the corresponding net and instance pin name in the parasitic file. A parasitic file should have one-to-one correspondence with the design. If not, then what may happen is that some of the nets will not get parasitic data. So when reading the parasitic file, by default PT assumes that the capacitance inside SPEF does not include the pin capacitance. The pin capacitance value always comes from the standard cell attribute. So again delay has two parts: cell delay and net delay. A cell, what properties does it have? A cell has the delay is represented in the lookup table, but it also has capacitance on the node. Each input and each output of a cell both have some inherent pin capacitance, and that capacitance value goes in the standard cell library, not in the spec. A spec will only contain interconnect data, not cell data. Although it would connect, so it will tell us what the nodes are. So for example, in this case, let's see this design. What the spec will contain? It will contain this node, instance name /z pin, to SDFF1/CP pin, and this is one net. So it will contain the RNC value of this net, but the inherent capacitance value of the bus at Z and of the flip flop at CP will come from the standard cell library still, right? So just the thing to remember here is that parasitics, SPS, SPEF or DSPF or RSPF, they just contain the interconnect data. That's it. So the reduced and detailed parasitic RC networks specified in spec file are used to compute effective capacitance. We'll talk about what effective capacitance is. So this is a part of delay calculation. So the capacitance value, this is most important thing. This you should sorry. Yeah. This is the thing that you should remember. The capacitance value reported by most report commands such as report timing or report net is the lumped capacitance. What it means is that now an interconnect will have multiple segments, but during the process of delay calculation, what PrimeTime will do, it will calculate a single value, which is the effective capacitance. This is to speed up the delay calculation, and it will show this value, this lumped value, when you do a report timing or do a report net command. It will not show us that how did it calculate the effective capacitance. It will not show us how many segments were there. It will not show us what algorithm it used to calculate this value of C factor. So we have to note that the value of capacitance we see in any of the commands we do is the lumped capacitance or C total. C total is the sum of all capacitance value of a net. So usually in most of the cases it is the sum. In case of NLDM, I think it's the sum, but I have never verified whether for a particular net that all the capacitance inside the spec plus all the pin capacitance is C total the simple sum of all or not. I'm not sure, but again the thing to remember here is that any report you do will report a single value of cap at a particular node, and that will contain the effect of the pin cap plus the net cap. Now let's come to delay calculation. So to perform STA, PrimeTime must accurately calculate. So what PrimeTime calculates is first it calculates the delay through each cell, whether it be combinational or sequential. It needs to calculate the delay for AND gate from pin A to pin output, from pin B to the output. For sequential cell, it will be from clock to Q. And second thing, at each node it needs to calculate the transition. Why? Because again the delay depends on the transition value. For example, the delay at the output of an AND gate, a 2-input AND gate, will depend on the load at the output plus the transition at input. Again, so there will be, let's say there is one buffer, let's say driving another buffer. So to calculate the delay here, to calculate the delay is at this point, PrimeTime needs to know the transition at this point plus the load at this point. Again, to know the transition here, PrimeTime, this transition here will be some function of the transition at this point. Again, delay is calculated at this point, and transition is calculated at this point. So at every node, prime time needs to calculate delay and transition both at every stage. A stage, any stage, it comprises of a driving cell, the RC network in between, and plus the receiver cell, the network, the load pins, right? So what is the goal? The goal is to compute the response at driver output and at the network load pins, given what is given value, given the input slew. Input transition is a requirement for prime time to calculate the output delay plus the output transition. Let's see a figure which will explain it all. So let's see, for example, on the left hand side you have a netlist. It is a simple circuit without any RC value. When it goes to physical design, it will get the RC values, and the network will look something like this, the one on the lower end, with different R values and different C values, right? So on the upper, on the top, the figure does not have any R values, only the C values. So this tells us the C. So these values are the ones that are coming from the library. These values, these are the pin cap values which are coming from the library itself. Here, this R value, and this C value, they come from the spec, from the parasitic data. So when we have the nonlinear delay model, which comes from the standard cell library, so standard cell library will define some lookup tables for delay and transition both. This type of model is called nonlinear delay model. The nonlinear delay model is slightly going out of use. Present day in lower technologies, 65 nanometer and beyond, CCS, constant current source model, is most popular, but that is outside the scope of this course. So we will only talk about nonlinear delay model. It does not, as a synthesis and FPA engineer, you don't need to be concerned a lot about which model is used, either NLDM or CCS or something else. We are more these are tool related things, and they go in conjunction with what is the library, who is the library vendor, what is the parasitic data, and so on. So we should just know about it, what is being used. You can go ahead and read about the CCS, but the more important task at hand is how to define the constraints, how to make sure that a design is fully and properly constrained. That is the goal of STM, right? And next step, we should know how to solve the timing variations. That is the next step before signing off. So we'll talk a bit about NLDM. So in case of NLDM, any circuit, let's say a circuit like this, prime time will divide it into three parts. One is the driver model. So let's say I have again a buffer driving a buffer. So this buffer is a driver. It will be represented by a driver model. This interconnect here in between will be represented by a reduced order network model, and the buffer, the receiver buffer here, the load buffer here, will be represented as receiver model. These three things here, they tell us that the fan out is free, for example. Now the driver model is intended to reproduce the response of the driving cell circuitry when connected to arbitrary RC network. What it means is that the driver model of a buffer, for example, should be independent of the interconnect drive. Where does the driver model come from? The driver model comes from the standard cell library, right? So here at the driver level, prime time will calculate the waveform. And where does this waveform come from? It comes from some load here. So this load here is the pin capacitance and the input transition. Now this input transition would be a result of a previous stage calculation, or it is a primary port and you have set input transition here, whatever. But this is the driver model For NLDM, this driver model should tell us what is the waveform role, what is the nature of the waveform role. That's it. Now the receiver model is intended to represent the complex input capacitance. Why complex? Because the capacitance there is not a fixed value, and it just depends on how the this is what is more accurate in CCS when compared to NLDM, this calculation. So it represents the complex input capacitance of the cell input pin, of this input pin, of this buffer here, including the effects of rise fall direction, the transition at this pin, slew or transfer, same thing, the receiver output load, the state of the cell, and then so many things, right? So the receiver buffer here is reduced to a single C effective value. So this value here, C, is nothing but the C effective value. The reduced order model, the network model, this one, is a simplified representation of the full parasitic network here. So this is where prime time will employ some algorithms to calculate the delay through this RC network. So any network, any parasitic network, whatever comes from SPEF will get reduced to a very simple circuit, which prime time will use to calculate delay. So please spend some time in reading this and understanding this. How does the prime time reduce a network and represent it into a driver model, a reduced order network model, and a receiver model. Now let's talk about the effective capacitance. So what is effective capacitance? I summarize again. Effective capacitance is a single capacitance value in case of NLDM. Please note that effective capacitance is very specific to NLDM. Is a single value of capacitance which is used to represent the load, the fan out load of a single cell, right? So effective capacitance approach is employed to handle the effect of both R and C. It is a single capacitance that can be utilized as an equivalent load. So in this case, the RC interconnect. So what prime time will do? It will reduce this RC interconnect into something like this, where C effective, where this is the driver model and this is the C effective. E effective is nothing but a single cap value which will replace the load, right? Now effective capacitance, as we discussed before, is a function of so many things. So this is, let's say, one particular graph where the total capacitance is mapped, the actual load is mapped, and then effective capacitance is calculated. Now we see that there is obviously some difference. So this effective capacitance would be different from the total cap. So total capacitance, I guess, would be the most inaccurate, because it will not take into effect. It will just be the sum of all the capacitance. It will not take into effect the rise and fall transitions and so on. The actual load, I guess, should be most accurate, because it will be segmented load. Whereas effective capacitance is something that STA tool calculates to make the job faster, calculate the delay faster. Otherwise, it will be as good as 5. So the idea, the aim behind STA tool calculating C effective is first to make the delay calculation faster, and second, it should not be too inaccurate. It should be within some percentage of the size calculation. Right? Usually, they will target about 2 to 3%. Third is the Elmore delay. Elmore delays are applicable for RC3. So this is what Elmore delay is, a very basic formula used to calculate the delay of an RC3. In case of when you read SPEF, prime time will not use Elmore delay. It will use some other calculation, which I am not sure about what it is. You don't need to worry about that. Only when you read in a reduced parasitic format, an RSPF, only then prime time will use Elmore delay, because Elmore delay is a very crude approximation, and RSPF on the RSPF does not contain a lot of parasitic data. It already has a reduced format. So Elmore delay is applied only when RSPF is there. It has a single input node, does not have any resistive loops, and all capacitances are between a node and a ground. For such networks, prime time will employ Elmore delay. Let's see what Elmore delay equation is. So any network which has R and C, so any network which can be segmented into such case, the Elmore delay is the delay through the first section is C1R1, the delay through second section is so if we talk about the delay through at 1, it will be C1 into R1, at 2 it will be C1 into R1 plus C2 into R1 plus R2. So at any node it will be, so this is the generic formula, TDN is equal to summation of Ci and then each of the capacitance multiplied by the sum of all the resistances seen by it. For example, at Ci the delay would be C1 R1 plus C2 R1 plus R2 plus Ci minus 1 Ri minus 1 plus R1 plus R1 and so on. At node I it will be Ci into, so assuming all the R values are same, R1 let's assume everything to be R, so it will be Ci into n times R plus Ci minus 1 into n minus 1 times R and so on. So this is the equation for Elmore delay. Again, this is a very basic formula, might not be very accurate, but it's used by prime time when you read RSPF. Now there's a very interesting case of slew merging. Now at any node like let's say a NAND gate here at Z, prime time can have only one transition value. Prime time cannot maintain multiple transition values at every node, otherwise this will blow up the delay calculation time. So prime time maintains only one value. That value will have two limits, max and a min. So in fact two values, but the max and a min. So now the transition at Z will depend, since it has two input pins, the transition at Z will depend on both the transition at input A and transition at input B. So for example, so now depending on the type of timing analysis, whether it's a max or a min, which of the slews will get propagated, that is the problem. So it will have two delays, it will have delay from A to Z, delay from B to Z. These delay values are separate, but the transition at Z can be calculated using the transition of either A or transition of either B. Now there is a variable in prime time called timing slew propagation mode. It can be set to one of the two values. Now let's say we are talking about the max path analysis. We have discussed already what is max path analysis. Max path analysis is used for setup path, setup constraint checking. It is usually done in it is more critical in worst case library when we consider worst case scenario, worst case operating condition. So there can be two, the variable can be controlled to select which transition number would be used to calculate the transition at Z. One is the worst slew, other is the worst arrival. What it means is that, now let's say this is okay, this is A, this is B. Now let's say A has or B has a better slew that when compared to A. So when we set this variable to worst slew propagation mode, prime time will calculate the value of transition at Z using the transition at A, because A has a worst transition. This is the most pessimistic mode, and you should be using this almost always. Why? Because in this case we are not worried about whether. So now the second mode, when I'll talk about second mode and then we'll know why this is pessimistic. The second mode is worst arrival. What it tells us that, what it tells prime time is that whatever arrives later, use that transition. This is a slightly more accurate analysis. Why? Because now let's say B arrives later. So typically the critical path would be through B. Why? Because B is arriving later. Since the delay at B is more, so the critical path, the setup critical path would be through B, and ideally it should use the transition at B. But when you use this the variable and set it to worst slew propagation, even if B is arriving later, it will use the transition at A. So it will always get a worse value. In this case, so in most of the cases we use this. This will make the analysis a bit more pessimistic, but we are okay with it. For min path, for hold timing calculation, it will use the best slew or best arrival. So when we set the variable to slew propagation, it will use worst slew for max path. It will use best slew for the hold. For setup, it will use worst slew. For hold, it will use the best slew, which is the more pessimistic analysis, and it is more suitable. It's good to have. So I think the default value is slew propagation. So the value can be the slew propagation or arrival propagation. When you use slew propagation for setup, it will take the worst slew. For hold, it will take the best slew. So this is please don't worry if you don't get what I'm talking about. This is a slightly advanced technique. This is a slightly advanced topic, and once we go to lab, I'll show you how does it affect. So when you see this thing happening in the lab, you will understand it better. The second problem about transitions is these are all problems that come in delay calculation. That's why we are discussing this. These are all issues with delay calculation. So other problem comes when there are different slew thresholds. We've already seen what slew thresholds are. Slew thresholds are the limit values between which the prime time should calculate the transition values. They can be 2080, 1090, 3070, and so on. If you have cells, so if you are sourcing standard cells from only one single library, all will have the same threshold. So there's no issue. But let's say U1 is from one library, U2 is from other library, U3 is from some other library, and these might have different slew threshold values. In this case, we don't have to worry a lot. Prime time does a good job. It will see what is the threshold value at each cell, and it will calculate it properly. For example, let's take this example. U1 is characterized with 2080, U2 has a 1090, U3 has a 3070, and a slew derate of 0.5. Derate simply means that multiply that factor by the slew value. Derate means that whatever slew value is calculated will multiply by 0.5. Now let's say the slew at Z is something. This is the slew at Z. So slew at U3A and slew at U2A are calculated. How they are calculated? First, the waveform is plotted, and after plotting the waveform, what peak prime time will do? For example, for U2, it will now take the 1090 numbers. For U3, it will take the 3070 numbers, but it will multiply that value by 0.5 because the rate is 0.5. The delay calculation is simple. Delay calculation is simply 50% here and 50% here. This is the difference. This is the delay. But the transition numbers get calculated based on what are the slew thresholds. So it is okay to have different slew thresholds, although it's not recommended. Delay calculation will become much more simpler and much more accurate if we use libraries. So a particular library vendor will make sure that all his cells have same threshold number. This is to make delay calculation simpler and more accurate. Right? Okay, let's move ahead. So this is a formula which tells what is the slew. What is the relationship between 1090 slew and 2080 slew? So you can also do this yourself. A simple formula: slew 2080 divided by 0.8 minus 0.2 is equal to slew 1090 divided by 0.9 minus 0.1. So if you know the slew at 1090, you can calculate the slew at 2080. Obviously, the 2080 numbers will be less than the 1090 numbers because again the region between 2080 is less than the region between 1090. So how the combination part delay is calculated? We did one example when we were calculating the clock latency in the last lecture. So for example, the prime time wants to calculate the fault delay. So every node will have fault delay and write delay because not the cells, the standard cells and nets are not symmetrical in terms of rise and fall. So each node, in fact, each node will have 4 values. In fact, it will have a rise value and a fall value, and for each rise and fall value, it will have a max value and a min value. We'll see how max and min comes into play here. Just please note that every node will have rise delay, fall delay. For rise delay, it will have a max value and a min value. For fall delay, it will have a max value and a min value. So for example, the fall value at this point, at this node, the final node, will be fall here would mean rise at fall at n3 would mean rise at n2, fall at n1, rise at n0. So it will be Tn0 rise, Ta fall because Z is falling, Tn1 fall, Tb rise because now Z will rise, Tn2 rise plus Tc fall again. This is a very simple equation, not much to worry about. You can read about it. So every node, so to calculate the rise delay at any node, runtime will go back to the first input port or to the first sequential cell it encounters. So again, remember, it will break all the complete design into different timing paths, and then for each timing path it will calculate the delay. This is how it calculates the delay. Part 2 flip flop, again it is very similar to how the delay is calculated for combination. There is no difference here. The mechanism, the algorithm, they are all same. The only thing for a flip flop, the only extra thing is the calculation of T setup and T hold constraints, T recovery, T removal, and so on. There are constraints in sequential cell. There are no constraints in a combinational cell. So again, it is same. So this slide, the two slides, what they are stressing the fact that prime time will care about unitness. That means what is unitness? An inverter is a negative unit. That means a rise at n0 will cause a fall at n1. A rise here will cause a fall here. A buffer is a positive unit. A rise at the input of a buffer will cause a rise at the output of the buffer. So prime time will worry about the unitness. It will calculate the delay according to this. It needs to know the unitness. That is why you see that if you go back to the standard cell library, you see any timing table, you see that it also mentions the unitness. So for example, a NOR gate is a negative unit, AND gate is positive unit, and so on. Right? So you just have to see what is the relationship between input and output in terms of when input rises, does output rise or fall, and that defines the unitness of the path. Now there are multiple paths in a complex design. Let's consider a flop to flop path like this. A flop to flop path like this might have multiple timing paths. The path that takes the longest is called the worst, late, or a max path, because that is critical for setup. So for example, here this dotted path is the worst path. It is the longest path. Longest path is used for setup calculation, for setup check. The min path, the shortest path, is used for hold timing check. Now in the last session, the last slide had one exercise where you had to calculate the setup and the hold slack, and in that I have mentioned two values, the max value and the min value. So this is why every node, this is one reason why every node will have a max value and a min value, because there are multiple paths through number of cells. Right? And any complex design will have, any design you do any design, you will find out that between two registers or input to register or register to output, there might be multiple paths. So not two paths, there can be 10 paths, there can be 20 paths, but prime time will calculate path delay through every node, and it will note down the, so it at deep end it will note down what is the worst arrival for rise. It will note down what is the worst arrival for fall. It will note down what is the best arrival for rise, what is the best arrival for fall. This will become very clear in the lab. Just please note, this is just to stress the fact that there are multiple paths, and what prime time worries about is the longest path and the shortest path. Although you can actually trace through any path, but the longest and the shortest will mean most for the setup critical path and the hold critical path. we saw what is slack calculation. This slide just again repeats that slack is the difference between required time and the time when a signal arrives. There is one example where, so this is the one example where this slide will calculate the slack here. The period is 10 nanosecond here. The data arrives at 1. The setup time here is 3. Data required is 7. So 7 minus 1, the slack is 6. This is how slack is calculated. We will see a lot more of this in the lab. Right. So that's all for this session. So again, the focus of this session was to make you all familiar with the concept of interconnect. The fact that interconnects, there are different formats for interconnects like DSPF, RSPF, and SPF. SPF is the most popular interconnect format. The data contained in interconnect format is only the RNC values of the internet. It doesn't have any cell capacitance value. That is important to know. And then we know that when in case of NLDM, prime time will model the network as a driver model plus the reduced interconnect network model and plus the receiver model. The receiver will be modeled as a single capacitance, or well, not simple, but a single effective capacitance called C effective or C total, which will be showed when you do a report timing minus capacitance. And then we saw that for transition calculation, okay. So first we saw that at every node prime time needs to calculate the delay plus the transition value. We saw that what are the problems that can happen during transition calculation. One is the skew merging. This is one good thing to know. Second thing is there can be different skew thresholds. And then we saw that there are multiple paths, and for each path prime time will calculate the worst path, the longest path, and the best path, which is the shortest path. The worst path is used for setup check. The best path is used for hold check. Right. This was all about interconnects and delay calculation. In next session, we'll see we'll learn a lot more about clocks and exceptions. Thank you.